Hello, my name is Qasim Anis Liahvi, and I will talk about the components and materials that we have used in our project for the self-driving car. At first, we have four motors and a Raspberry Pi, and also we have a camera and a camera holder 3D printed. Also, we have wires, female and male wires. We have this H bridge for the motor driver. We also used the power bank to get power for the Raspberry Pi. Also, we have a three battery, and each one is 3.7 volts for the motor to make it work.
Hello everyone, my name is Mahmoud. I'm going to continue to explain the connections of the car as my partner Qasim explained the components. So basically the connections of the car is as the following. As we have here the Raspberry Pi, it's getting the connections from the pins of the Raspberry Pi to the H-bridge. The H-bridge contains only two motors. We connected two motors from here to one slot of the H-bridge and the same to the other side. As you can see here, the batteries are connected directly from down of the car, which are there here. There are three batteries here, and it's connected directly to the H bridge that are getting the connection from here. And there is a common ground coming from the H bridge to the Raspberry Pi. So basically, as you can see here, is that the Raspberry Pi is getting the power from the power bank. The power bank can give an output of 5 volts 5 volts 2 ampere, which is enough for the Raspberry Pi to operate. So as you can see here, it's getting the camera from the Raspberry Pi to here. We get a 3D printed part for the camera mount, and so it can be high and can detect, and we can also modify it as the way that we want. Right, left, also up and down. So from here, as you can see from the up, I can see detection, which is coming from the camera. When I move it, it's going to go up and down, and he's getting the heading image. Thank you very much.
Hello there, my name is Ahmed Zaitoun, and I'll be explaining the code for the Raspberry Pi. So first of all, we import the libraries that we're going to need. Okay, so I imported all the libraries that you can see here. We set the warnings to false, so we don't want to get any warnings. We don't want the code to either stop working in case there's a warning, so we just ignore them. And we define the pins, and remember the GPIO numbering is different from the physical pins, so 22 actually is the physical pin 15. Okay, so we set the pins for each motor and their enabled pins as well. Okay, once we do that, we just set them up as output. Alright, and then you don't really need this. I added this by mistake, so just ignore this high-low, okay, along with the timer stop. So this also you don't need. Okay, alright, now we also set the pulse width modulation to 1000 Hertz. I found that to be working the best with the code. Okay, we make sure the motors are not working, they're stopped, and we set a timer for 1 second for it to process. And now we move on to all the the functions that we're going to be using. So we're going to use the first function, which is detect line segments. So over here, I'll just explain the variables. So RHO, it is the distance precision in pixels. Usually it's 1. The theta would be the angular precision in radians, which is pi over 180, so 1 degree. The min threshold would be the minimum volts it should get for it to be considered a line. Okay, so we do the Hopf transformation to detect the lines from the etched frame. Okay, the technique is basically to detect any shape in a mathematical form. Okay, so for this application we use the cv2.hofline_p function, which is used to detect lines in each frame. Okay, all right. So the function would retain an endpoint of a line. Okay, and the average, slope, and intercept, and which is found here, this function under it. Okay, what it does basically is that you recall the equation, which is y equals mx plus b, so where m is the slope and b is the y-intercept. So this part we're just doing the same thing. We're taking the average of the slopes and the intercept of line segments, detecting using the Hopf transformation. Okay, this will be calculated, but before doing that, we're going to be taking each frame and doing the calculation for it. Okay, the left lane appears to be going upward, so it has a negative slope, right? So remember the coordinate start system point. So in other words, if the left lane has an x1 less than x2 and y2 less than y1, which I'll be going over the if statements right here. Okay, I'm going to be explaining this part. So in that case, the slope would be y2 minus y1 over x2 minus x1, which will give us a negative slope. Therefore, all lines in the negative slope are considered to be left lanes. Same thing, but the complete opposite for the right one, okay? If x2 bigger than x1 and y2 is bigger than y1, this will be a positive slope. In other words, all lines will be positive, and it will be considered right lane. Okay, in case of vertical line where x1 equals x2, the slope will be infinite. Okay, to skip all the vertical lines and prevent getting an error, to add more accuracy to this section, each frame is divided into two regions, right and left region, through the boundary lines. Okay? Alright, now the next function, let's go over that. So we have the make point. Make point is basically a helper function. Okay? What this function done is basically return the bounded coordinates for the lines from the bottom to the middle of the frame. And to prevent dividing by zero, which is a condition that will be presented during the run of the code. So if slope equals zero, which means y1 equals y2, the horizontal line, it will give the slope a value near zero. This will not affect the performance of the algorithm, as well as it will just prevent the case from happening, which is dividing by zero, which will inevitably give us an error, right? We're also using the right here, the display lines. Okay. So display lines basically has the cv2.addWeighted function to take the following parameters, and it's used to combine two images, but giving each one a weight, and then it will calculate the output image using the following equation, which is the alpha multiplied by the image 1 plus beta multiplied by the image 2 plus gamma. Okay? Alright, now we have the get steering angle. So we're going to calculate and display the headline. So in this final step, what we'll do is basically the headline is responsible to give the steering motor the direction it should go to. In our case, there is no such thing as steering motor. We're just using two motors to turn right, two motors to turn left, and four of them to go straight ahead. So let's go back there. So if we want to calculate the headline, it's a pure basically trigonometry. So tan and arctan are used. Some extreme cases are when the camera detects only one lane and it doesn't detect any other line or lane. So in that case, what we want to do is basically call this function to prevent that, or to make the code still work despite the given case. So x offset in the first case is how much the average right x2 and left x2 are divided by 2. The first from the middle of the screen. And the y offset, same thing, but it's for the height divided by 2. Okay? So what we're saying is, let me just scroll down a bit, yeah, right here. So what we're saying is, if the steering angle equals 90, it means that the car has a heading line perpendicular to the height, height over 2 obviously, line, and the car will be moving forward without steering. If the steering angle is is bigger than 90, the car should steer to the right. Otherwise, if it's less, it should steer to the left. To display the heading line, we just use the code that you see here below in this function. Okay. Alright, the function above just takes, the frames in which the heading line are will be drawn, and then we'll take the steering angle as an input and return the image of the heading line and the heading line frame taken, from the image above, which is, would be the frame that we took here, Okay. Then we start capturing the video. We set the video to be 320 by 240, and we put the code in a while loop, so it continuously run until you stop it or physically stop the motors. Alright, now moving on here, you can see that we have an if statement where that if the escape button is pressed will basically stop the car. Under that we have the the color thresholding. So in that case, I'm just basically thresholding for the red. Yes, it says lower and upper blue, but really I'm just detecting the red here. Alright, we use the SV2 CVT color to turn it from RGB to HSV color space, and then we mask it and we apply the edge to the frame. Okay. After that, we set the region of interest, as you can see right here. So here we set the region of interest to just have the screen. And we merge the region of interest by using the bitwise AND. Okay, and here we can see that we are actually calling the functions above, and then we're using the PID. So the PID, how it works? Well, this is how it works. Okay, so we have a set point defined, which is needed for the system to reach, and the error is calculated using error equals set point minus actual. Let me just scroll down. Okay. Alright, so right here. So the P, which controls the proportional error value. So if error increases, P has to also increase. I will control and integrate, the error over time. Okay, but increasing it will probably cause to overshoot. So D works in slowing down the time derivative for the error. In other words, the slope of the error will be is slower to be increased, you know. So yeah, sure. Okay, thank you. All right, just give me 5 minutes, okay? Sorry. So as I was saying here, we just calculate the deviation from the center lane. If it's between 5 and -5, we just go forward in speed, which is 60% speed of the motor. If it's less than -5, then we steer right, and if it's more than 5, then we steer left. Okay, and here you can see the calculation of the PID, okay, and the speed as well. Once we're done, and if we skip escape, we just destroy all the windows and we release the video. And that would be the end of the explanation.